thank you for the introduction, because the introduction really was sort of the introduction for this talk too, because this idea to make community modeling more, not just do it with a few models, but do it everything, that's really the background to the unified forecast system. And so if you notice, this is not a background with a NOAA background from the slide, because the unified forecast system is a little bit outside of NOAA. And just recognize that the steering committee of the unified forecast system is me and Ricky Rood are the two chairs of that. And so a lot of these slides are collaboration between many of us. So the whole idea of the UFS is to do business a little differently. When I joined NOAA about 25 years ago, and you don't have to call me Dr. Tolman, I'm not that old. At that time, we had the biggest computer, we had the most people. And so a lot of the work we did was done in-house with our own models. And at that time, that was not a question of us being egocentric or anything like that. It was just the reality of we having the resources, so we could do it that way. If you look at it right now, our computers are barely in the top 200. There's much more computing available at NSF, DOE, DOD, and in the cloud. And so the idea of us being able to have the best system in the world with just our own resources is just laughable right now. So we need to change the way we're doing business. And so this slide here is basically telling you the real differences we have with all these things. So the whole idea is to have a community developed Earth modeling system is a little bit different from doing making your model a community model. So it may sound almost the same, but the idea of using a community model for doing modeling rather than making your model or trying to make it a community model is huge when you talk to NCAR and other folks like that. The idea to move R2O quicker is behind that. We really want to do that. So that means that you have need some governance, both for maintaining the code to begin with, but also to figure out what goes into operations. We've got dinged for many, many years of not doing evidence-based decision-making for that, which I think is our mistake of not communicating how we make decisions more than that we actually not doing evidence-based decision-making, because we are doing that. But it has to go two ways. You cannot have somebody from the outside saying, prove to me that you're doing the best thing, and then turn around and say, you should take my stuff, believe me, and leave it at that. The idea of the UFS is to have a single software stack that can be configured into different applications, and come back to that a little bit later. The UFS, if you look at what it says, it is a unified system, which is not unitary, it's unified. What we mean with that is that we share particularly infrastructure and also science components. The idea of this is to have a better business model for both science and R2O. The idea is that if you let every scientist do their own work, then you get a lot of good papers, you get a lot of ideas about details of a very complex forecast system. But if you want to make the forecast system itself as a whole better, you have to have focus on a few of these systems. And so the idea of a unified forecast system is to find a better balance between having focus on working on just a few things, while in the meantime retaining as much diversity as you need to be able to do good research. And so the impact of this thing, it is really a massive paradigm shift. We are really going to rely on the community developed models and community software to get that into operations and to much accelerate the way things go into operations that way. So the idea of what we do is looking at the fact that you have things that go from nowcast to hourly forecast all the way to essentially full climate. And so the things that we're looking at is much more than just weather. So on the top line here, you see a bunch of the weather systems we have right now. And then it's much more. So it's weather applications like hurricane, it's weather applications like space weather, but it's also including marine air quality, floods, hydrological, and you can go a step further with that too, because marine ecosystems fits in here too. Actually, I held a workshop in late 2007 when I became Marine Branch Chief, and even at that time, 12 years ago, we said that at some point, especially the lower tropic level marine ecosystems need to be part of the physical model, because it has a direct two-way interaction between the physics of the environment and the marine part of the ecosystem part of it. So also it isn't called out here because this is sort of a high level part, but in the marine and the coastal side, that's where sea ice lives for us mostly. Then to go a step back, because we say that we want to use the UFS for operations, and so it's kind of interesting to see where it came from. The upper left is what I lovingly call the Quilt. This is a highly simplified version of a highly simplified version of a highly simplified look at what we're actually running in operations. There are 25, in 2000, the last time I had a hard count, we were running 25 major forecast systems that were needed to be transitioned from a vector machine to a parallel machine. And we were running some 1,600 codes in support of that. And the reason why you get this really complex system here on the left, which includes sea ice as part of some of our products, as well as part of some of our ocean models. The reason why we got this is because our governance of how to run the operational system was basically focused on individual solutions and not on a holistic way of looking forward. So with the reorganization of the Weather Service a few years back, we separate these things out now. We separately look at what our requirements are for our operational people, and then we're trying to look separately from separate from the people who do the requirements. There are people who look at the solutions, which is essentially my office where I'm working for. And with doing that, you can basically come to the conclusion that you should have your production suite arranged along lines of products at different scales. And so if you think about that previous slide I showed with from hourly to seasonal, the bottom right is what our production suite is supposed to be looking like. So organized around products at different time and space scales. And so believe it or not, but that thing on the left top with all its complexity can be moved to the right. And this is basically having all major bits and pieces in there. And so from the ice side, no, we don't specifically call out waves, we don't specifically call out ice, we don't specifically call out ocean. But the idea is that every single scale that we're looking at, even at the shortest time scales, there are aspects of coupling that are really important for getting the next level of accuracy for our systems. So we've worked for 50 years on just standalone weather models, standalone ocean models and things like that. But the idea of the community is that if we want to have sustained improvement of all our forecasts, we really need to do all these things in a coupled way. And on top of that, we need to make sure that all of these things are ensemble based, because from a forecast perspective, telling about the uncertainty of the forecast is just as important as the forecast itself. And then all these things, especially the longer time scales, need some kind of reforecast and reanalysis, because there's a lot of additional accuracy you can get if you can correct on the fly your models for the systematic errors that they have. So in terms of governance, the thing that is really different, and I mean, there's hundreds of ways of drawing this, and you can move the circles a little bit if you put people like central operations from the Weather Service in there. But the idea that the production suite is really a subset of a bigger community model where we decide what is ready on our side, but where the development is really driven by the community more than by us. And then the idea that we have a lot of partner organizations and not just us. And to give you an idea of that, some of the infrastructure that we're already using has been done long ago in collaboration with organizations like NASA and others. So it's way more than us. And by the way, I came from NASA before I went to the Weather Service too. And so the idea is, like I said, doing a community-based model and bringing it to operations rather than the other way around. May sound to a lot of people as a small detail, but it's really pretty revolutionary in terms of how we've been doing business in the past. And so in terms of governance, so governance is a little bit a work in progress. And it's basically a work in progress because we've been bringing in the community quite systematically. The key of this is what we call the Strategic Implementation Plan working groups. So there are 13 topics that we identified as needing attention in terms of having a plan to go forward. And these strategic implementation plans is basically telling us what we're doing with next year's funding and looking ahead 3 to 5 years. These groups, all of these groups have a federal and a non-federal co-lead, or sometimes more co-leads. And there are roughly about 150 people involved in all these teams. So where if you realize that the Environmental Modeling Center only has about 20 or so leads, it is very obvious that we are now much more driven by the community in terms of even planning what we're doing in operations and what we need to do in terms of short-term research. Then next to that on the left side is the steering committee that is having by definition, my job position as the strategic lead for modeling in STI gives me that position, and our external person is Ricky Root from University of Wisconsin, who we actually funding to actually spend like about a third of his time or so, a quarter of his time on this stuff full time. And then the steering committee meets every month, and a measure of success is that, every week on Friday at 11 o'clock. It is a open meeting, although if there's any voting needs to be done, there is a core identification of who has a vote. The fact that we have 40 to 50 to 70 people on that call every Friday should give you an idea that this is way more than just a nice thing on paper. It has really been a lot of buy-in just from the people that are there. Then on top of that, we have a technical oversight board that meets probably about once every 6 months. These are really the people with the money in the different organizations. So it started off within NOAA with having OAR and the Weather Service talk to each other and leverage each other's money. But it has people like NCAR in there, it has people like NASA in there, and anybody who is interested in this kind of a modeling approach and has some funds to work on that. So we want to make sure that these program managers on a very high level understand that they need to leverage each other's money to be efficient in an approach like this. And I call this a work in progress because this is a heck of a lot of time that we spend on meetings between all kinds of teams. And so we're actually trying to look see if we can simplify this a little bit, particularly on the execution side, because at the moment, most of the execution side requires work plans for individual little projects. And so we're trying to figure out how we can do this governance in such a way that between the organizations, we do the work plan level at a little bit of less granularity to make sure that our lead scientists and the managers are not spending about 60 to 80 hours a week on writing plans and reviewing them. A really big issue of this is the fact that we have buy-in from the research community, as is evident from the fact that we have a formal MOA between effectively Weather Service, OAR, and NCAR. We spent a year discussing these things, and we came up with 7 concrete infrastructure issues that we wanted to work on. If you really simplify this, you say this is trying to get the UFS and the CESM working off the same infrastructure. Now, normally, if you write an MOA, we tend to be very much high-level hand-waving, and these MOAs usually end up on a bookshelf somewhere once they're signed. The thing that is unique here is that we actually identified software packages all over the place where and approaches from the 2 organizations that we wanted to work on. So this is actually an MOA that actually talks about the details of what we're working on together. And the interesting part is if you look at the capitalized terms on this page, about half were coming out of the NOAA side and about half coming out of the NCAR side, which is also a good idea of a good indicator that we have a real way of working together. And in fact, before this MOA got signed, we already had a whole bunch of people getting funding from both the NOAA side and the NCAR side on doing a lot of this work. And we can talk a little bit more about this later if you want to, but in the interest of time, I'm just leaving it at this one slide here. The other part is really important is that if you just have a software stack and you develop little bits and pieces of that, that's very nice. But for us, it's important to get actually real operational outcomes. And the difference between having a piece of software available for the research community to work with and actually getting real outcomes is to actually focus on true applications. And the applications is requiring some kind of workflow, but you can see here what the key bits and pieces are of all these applications. And so just one thing I want to point out here, that data assimilation is an integral part of the unified forecast system. So we're calling it a forecast system, not a modeling system, because at least there are a lot of people who think that you probably should even spend more time on data assimilation than actually the model. So What kind of applications are we looking at? For now, that is a little bit driven out of the operational side, but that is completely open to any of our partners to add to that. You can read just as fast as I can speak, and you can probably read faster. But the thing that is really important here, the top set is really weather focused. The bottom set, and this includes the cryosphere, are what used to be the downstream models in our operational suite, but which become the coupled components in the UFS, and so marine and cryosphere is specifically mentioned there. The reason why we talk out about 10 days is because we already in the subseasonal and the seasonal side have done coupled modeling for a long time on that, and so there is a focus on that. And so right now we're focusing on getting bits and pieces of our system into the unified forecast system, but the goal in about 5 years to have all these things in coupled modeling systems, so our forecast system, operational production suite becomes much simpler. So what does this look like in practice? So on the right side, you see one of the diagrams that looks at what an architecture looks like. And the thing to take home from this is that we've decided a few years back that we're going to do coupled modeling at such a level that we couple our models at sort of the outside of the model. So you either wrap it around it and put it into a coupling infrastructure. That allows you to keep the models, the component models, relatively independent. And whereas it forces you to do the coupling sort of on the outside of the model. In the long run, that may not be the best way to do it. In the short time, this is a decision, strategic business model decision. It allows us to work very hard on the coupling while we do not impede the development of the underlying component models. And so for the short term, we believe that that's the best way of doing it. And so the infrastructure of this could be fairly unified. We are actually looking at getting components and capabilities of different couplers into a single system so we can have a single infrastructure. Underneath this, we try to get as few as possible component models that we use in operations. And so right now, the component models on the infrastructure are the NEMS infrastructure, which becomes CMAPS, which is being developed right now at NCAR as an evolution of NEMS. We're looking at a common community physics package, or CCPP, that is being put in there. And then we use an FV3 weather die core, a MOM6 ocean model, and HICOM ocean model, WaveWatch 3-wave model, the CIS5 ice model, GoCard aerosol, and the NOAA MP land model. And just in terms of the infrastructure, the one thing I want to talk about a little bit, because it's not always understood, we're talking about ESMF, NUOPSI, and NEMS as a coupling infrastructure. So ESMF is the underlying language of the coupling, so that it tells you how you do the caps around your component models. That was actually for a big part paid for by NASA initially. So don't misquote me as saying that it's just that the UFS is just a combination of NOAA and NCAR working. So NASA, DOD, DOE, all these people are really interested in working with us on this. So NUOPSI is then defining the names of the different, standardizing the names of the different parameters. So it's sort of the dictionary that goes over top of the language. By having this NUOPSI cap over ESMF, you create a situation where it can really be plug and play. So HICOM and MOM6, you can pretty much exchange these models very easily in a coupled application because they use exactly the same language in their interface. And then NEMS is actually the book that actually makes all the things work together. And so each of these components has its own repository. And the nice thing of the NEMS infrastructure is that you can run say ice model as part of a fully coupled system in the NEMS repository, or in the NEMS infrastructure, but you can use exactly the same driver and switch the dynamic models for, say, ocean and atmosphere, with just an external data flow, and you can run exactly the same set of infrastructure and models that way for running just a standalone ice model or a fully coupled ice model. And this is really making the working with the component models independently and with the coupled system a really powerful way of doing further development. And so in terms of practical progress, the NEMS coupler was more or less and the things on the previous page were more or less fully functional about 6 to 12 months ago. And since then, we've had at least 6 of the prototypes here that are built for coupling that are actually at a level that they give solid results. So one of them is atmosphere wave coupling. One of them is atmosphere chemistry coupling. The ARCUS wave watch 3 is coupled wave surge coastal inundation modeling. Then there is a MOM6 sea ice coupled. There is a FE3 MOM6 sea ice capability, which is really the core prototype for our seasonal and subseasonal modeling. And there's a version of that model that has the wave model coupled in it too. I could spend another 3 or 4 hours just showing the results of these, but since we're in IARPIC right now, I'll give you a little bit of results from our coupled CIS5 MOM6 FE3 atmosphere ocean ice model, and comparing that to what happened with the CFS compared to the climate forecast system V2. We were running 45-day free runs with this model, starting from initialization from the CFS. If you look at the dashed lines here, the red and the blue dashed lines was what the total ice extent was in the CFS V2. If you look at the solid lines, that is this coupled model without any further tuning or training. You can see that in the Arctic, the CFS has a massive drift in ice results, whereas the UFS actually shows very reasonable results. Again, I say without any tuning. And if you look at the Arctic, the picture is even much more extreme. So you can see that specifically for the ice modeling, this coupled modeling is really looking like a really good step forward. And the takeaways of this whole thing is that we're looking at the UFS as a focus of all modeling in NOAA at least, and then hopefully with as big a community as possible. Helps us with shared understanding, shared investment, and have a good strategic focus. The governance is there. It's actually working, but we want to make sure that it becomes a little bit less of an overhead in terms of the time involved by senior leadership in all the organizations. And then I didn't really talk about this, but if you go to the UFS website, we published a few things on how to do R2O more efficiently, and that we take a look at the website if you're interested more in that. And then on top of that, we have in law, we have something called EPIC, the Earth Prediction Innovation Center, that we are told to set up, which is intended to do this kind of community modeling and to accelerate R2O. And so what EPIC is doing as it's being set up, and it should be fully in place by next summer, is really accelerate these ideas of doing a UFS approach. So the powers that be have come to the conclusion that we're on the right track in terms of trying to do a UFS, and that the EPIC wants to accelerate that. And so there's going to be a request for proposals for that coming out relatively soon. And it's not quite clear what EPIC exactly is going to do, but what I hope that EPIC is going to do is to create a support system for doing this community modeling between operations and the research community. And then as a last step before I hand the time back, this is really proven to be a concept that can really accelerate operations. Research to operations processes. And what we've done with this, we've test run this with the WaveWatch wave model for about 15 years. And we've test run this with the Hurricane H4 model for quite a while. If you take a new model and you put it into operations, it'll typically take about 5 years after the model has reached maturity in the research world. If you do a development in a already operationally hardened infrastructure, you can do it in 1 year or less. So literally using a UFS that is used for both research and operations can literally accelerate the R2O process of mature science and mature modeling capability by a factor of 5. And we've shown that with the wave model. The first wave model implementation took about 7 years. Last summer, Enrique Alves created a new Great Lakes wave model. We went from a regular grid to a unstructured triangular grid. We went from 2.5 kilometer resolution to 250 meter resolution. We put new physics in the model, and we put a whole bunch of new, about 60 or 70 new output parameters in there. In the past, that would have been a completely new model, and it would have taken 5 to 7 years to get in there. Enrique did that because all the research work was done with the community model, did it in under 9 months. So I'm a very strong believer in community modeling and having research done with the same tools as are used in operations. And I believe that is the single most thing that can help us to really accelerate getting stuff from research into operations. And it can be a massive force multiplier in terms of getting much more research into operations. And we've seen that with the Hurricane Forecast Improvement Project, where now we typically have 4 or 5 innovations that go into the hurricane model every year, instead of the only 1 or 2 that we could do internally, which resulted in, for the first time ever, have a sustained improvement in hurricane intensity forecasting. And so, thank you for listening to me, and I'm available for questions.
Thank you so much, Hendrik. That was a really wonderful presentation. I'd like to open up the floor for questions from those of you on the phone. Go ahead.
Do I need to hand leave it just open for now? I must have been really boring.
So can I ask a question?
Oh, go ahead.
Go ahead. Go ahead. Your turn.
Oh, I was just going to throw out a question while other folks were formulating theirs. One thing I think this forum provides a nice opportunity for is for you to provide any sort of advice you may wish to offer to folks from the Marine Ecosystems Collaboration Team who collect marine observations in terms of, number one, what are the mechanisms for providing observational data to assimilate into models? And then secondly, if you have any advice for observational scientists to think about as they design sampling programs in terms of useful scales of observation for enabling model verification and validation.
So if you look at your second question, I'm not often using the international community like WMO as a positive example, but WMO does something called Rollin Requirements. They used to do that through JCOM. So every few years we would look at all the type of observations we needed, and we would define what the accuracy was, what the resolution was, and what the cadence of the observations needed to be at 2 levels. The one level would be this needs to be the resolution, the cadence, and the accuracy for the data to be useful. And then having a second level of numbers that says beyond this accuracy and resolution, there's no new value. And so looking into what is done with WMO with these rolling requirements, and it's a little interesting what's going on with that, as the WMO is reorganizing and JCOM does not exist anymore in a few weeks. It is still a very good process to look at because I really like that idea that they did with establishing minimum and ideal accuracies and resolutions and cadences. How to do it practically, there's also 2 ways of looking at that. Your data does not have to be available for real-time use in an assimilation system to be useful. So the first thing to do is to look at the business model, how you do your observations. If it's a one-off or not quite operational, you still want to have that data available somewhere so we can use it for retrospective testing of all our models. And so one of the ways of going forward to that, I would suggest you start talking to the people that run MET at NCAR. They are becoming our go-to unified way of doing validation and verification of all our models. And so they would be a place to have, and in the discussions we have with them, we are moving away from only doing operational data to actually doing one-off data, because we want to get much more validation done on the process basis and not just on the outcome basis of our models. And so those would be people to talk to what you need to do to get your ecological data into their base database for doing all kinds of model validation. And then the third thing is, yeah, at some point, some of these data may be really useful for real-time improvement. And like I said already in 2007, the white paper of that workshop specifically calls out the lower trophic level ecosystem work as being directly influencing the physics of the model and the physics of the ocean. So ocean color and these kind of things are type of data that we would love to see in real time, because they would in principle be able to help us to in the future have a coupled modeling system that has at least a lower trophic level ecosystem in there, or at least ocean color in there, that kind of thing. And so that becomes a little harder to go on. I would suggest that you talk to the DMAC group in ARCUS. So NOS ARCUS spend a lot of time on how to get general ocean data properly standardized and properly routed to get in all these places. And don't reinvent the wheel. Talk to the DMAC group at ARCUS, and so go to NOS ARCUS first. And of course, the other thing is you have to go to the right meetings, right? For those of you who see the video, this is my Ocean Ops water bottle from earlier this year. Did that help?
That's wonderful, thank you. Other questions?
So Hendrik, can you talk a bit about the marine biogeochemistry capabilities that are, modeling capabilities that are present or enabled in UFS, if any?
I just told you everything. We have very little available at the moment. So so this is more dependent on the component models right now. So there are some approaches that for HICOM and MOM6, and also the other models that we're using is FECOM and ROMS are actually also two of the models that are actively used. There are some capabilities in ROMS to do ocean color, and we need to figure out how to do that. But just for the first time ever, we actually have a full-time paid marine ecosystem person at EMC to start looking at that a little bit more into detail. And so there has been quite a bit of work, but in the UFS, that still needs to be transitioned to it.
Okay.
And one of the things that has made I mean, I've talked with fisheries for a long time. I was talking to Mike Ford 15, 20 years ago about how to do these kind of things. And one of the things that has stopped us a little bit is that we were more interested in different timescales. So the fisheries folks were more interested in being able to do 20, 30 year stock assessments, whereas that's a little bit out of our scale. And so only about 10 years ago did we get a real high resolution ocean reanalysis that you could start looking at that. And of course, it was kind of funny too, because with some of the EcoSim and other models that they're running, Mike Ford was asking me for getting some access to our supercomputers, and then I realized that my desktop could basically provide all the computing he wanted to begin with. So it's kind of funny how that works. But yeah, this is still. I see fisheries being very interested in what we're doing with the UFS, because they are moving to a much more physical model-based approach to physical environmental model-based approach to the short-term and the long-term stock assessments they're doing. And I see like I said, the capability. If you look at some of the work about over the last 10 years, ocean color has about a signal with an amplitude about up to about 2 or 3 degrees centigrade in terms of ocean temperatures, and has a big impact on mixed layer depth and on total heat content. So we know that we are interested in it, and it's a question of being able to walk before you can run.
right. Well, thank you very much, Hendrik, for your presentation. I'd be happy for folks during the next discussion period to discuss things specific to Hendrik's presentation, but perhaps it's time to open up the conversation a little bit more broadly, and we'll just return quickly to the set of discussion questions that were posed at the end of part 1 of our webinar last month, to sort of throw some ideas out for questions that we wanted to pose to this group and see where the conversation takes us. So some of the things we asked were things like, how can we strengthen interactions between the observational and modeling communities? Are meetings like this a useful forum? What can we do to make it more useful? So please provide advice to those of us who organize calls like this year, so we can think about that going forward. Is there support for a separate self-forming team to look at this specifically? So a group for marine biogeochemical modeling. Is there sufficient interest that folks want to have their own monthly conversations just on this topic? Are there enough session opportunities at meetings like the Ocean Sciences, Alaska Marine Science Symposium, AGU, to allow folks from our respective communities to connect? And if not, can we identify some volunteers who'd be interested in helping make this happen? Could we potentially make progress by organizing workshops, and what might some mechanisms for that be? One suggestion was whether maybe folks thought the National Science Foundation Research Coordination Network opportunity might serve these purposes well. So I guess we'll start there in terms of what are mechanisms that folks think would be useful for advancing this conversation. Okay, well, another question that was posed at the end of last month's call was with respect to proposal calls. So do proposal calls by organizations like National Science Foundation, other agencies, North Pacific Research Board, do we put enough emphasis on requiring a combined observational and modeling approach to help advance this? And might that be one opportunity where we could make progress? Do folks have thoughts on that? Have you seen good examples in calls from agencies that try to achieve this, or is this an area where we could really improve? And if so, do you have any specific recommendations for that?
Yeah, there was recently a NASA solicitation as part of the interdisciplinary science program that was focusing on polar regions, high latitude environments, and they were specifically asking for integration of field observations, remote sensing, and modeling activities. And typically with NASA programs, and especially the interdisciplinary science solicitation, you see this integration.
If I can add to this, this is Hayo. I think it may be important to distinguish more clearly what type of modeling is referred to here. If you look at sustained observations or even episodic ad hoc, in some areas the science is mature enough, and the physics or the biogeochemistry for that matter is tractable enough that you can use observing system simulation experiments to guide your observational program design. But in other areas, that's not yet, or potentially will never be the case. And I think if you think about, in particular, the use of observing system simulation experiments, I would argue that more broadly, asking for observational programs or activities, campaigns to draw on a combination of appropriate modeling systems, remote sensing data, which may include quite a bit of guidance in terms of at what scales and over what spatial scales and over what time scales you most efficiently sample, as well as other sorts of expertise would be important. So that's just a minor caveat and a plea for clarification. Thanks.
Wilbert, it looked like you were going to say something. Please go ahead.
No, sorry, I was not planning to respond to that.
Oh, sorry.
I hope anybody else would have some comments on this. I mean, I guess also in the sense of the different agencies, they have different capabilities. Like DOE is much more focused on modeling than on observations, for instance. And it probably would be hard to add a funded component to that would be focused on observation, on gathering observations to support some process or so. And maybe that's the other way around for agencies that are more geared towards observational projects or so, that it would be a little bit more difficult for them to fund modeling activities in association with that. I don't know.
Yeah, recently DOE also had an opportunity as part of their terrestrial aquatic interface efforts, not just for high latitude environments, but across different latitudes, efforts focusing on terrestrial aquatic interfaces, exchanges between the land and the ocean. They were highlighting the need for developing new models, but also they were soliciting for proposals and projects that would integrate observations. So there is, I think there is a growing emphasis across agencies to highlight this need and actually have some funding directly for this kind of integrations.
Mm-hmm.
Yeah, and I would add to that it's getting better now. In the past, it was really the modeling, even in big project, would come in the synthesis phase. I remember several meetings where I pushed for not having them in the synthesis phase, but in the planning phase even, because there was a disconnect then between the modeling and the observationist. You had to use what the observationist had collected, but you had no input in the collection of the data. And sometimes there was this little, a change of if you knew better the water mass where they were going to, move your sites a few kilometers and you were in a better situated environment. But also the way of collecting or looking at the data, for instance, I remember that sometimes you get the chlorophyll from the fluorescence photometric measurement, and sometimes you get them from the HPLC. They measure different chlorophyll A or chlorophyll. Satellite is the same. And then you model something else even, or something in between, but you don't know necessarily what it is. And so it became very interesting to ask the observationalist to have a full dialogue of what the model is producing, what the model is modeling, and what the observations are. Primary production is another very good example. What comes from the estimate of oxygen is not necessarily what comes from the estimate of carbon. So those emphasis between modeler and observationalist are even more fundamental than trying to reproduce or complement the observation. It's really the basis of what is the model compared to what are the measurements. That's one thing. The second thing is once the data have been collected, they are still spread in different databases. And that is another problem. All the databases have their own little way of putting things, and sometimes you have to open 5 or 6 files before you can get the location, how they were measured, the quality of the data, if you get them all. So it would be worth getting a full workshop and write a proposal to really assess those fundamental questions if we want to make big progress. Otherwise, you can say, hey, look, I'm going to talk to my colleagues. We can have proposals saying, you have to have experimentalists with you guys. Still, you might not have the experimentalists that you have or observationalists that you need, because you cannot have one from the bacteria, one for the zooplankton, one for the phytoplankton, one for the dissolved organic matter on your team of modelers. Those proposals will be costly prohibited. So I think it would be worthwhile to get a serious group that focus on those fundamental questions. What are we trying to accomplish? Where are the data? Where are the model? What are the model into? Are they in carbon and nitrogen in phosphate? They are very different what they are going to give you. And to reconcile all the data with all the models.
Can I add something to that? So
Absolutely.
there are 2 sort of fundamental aspects to this. The one that was said a little earlier, the observation has been made, and the observations are on 100 different places, and they're not unified in anything like that. And so I would really suggest that, like I said earlier, we were in that situation with the physical oceanography about 10 years ago. And this IUS DMAC group has done a fantastic job on that. They set standards, they created clearinghouses, and it's basically, you can get all the data in one place now. So, but that's sort of the backside of the problem. On the front end of it, it's one thing to say that a model should work with an observationalist, but that's pretty much a hand-waving thing. Or if you say it the other way around. I think that if you want to systematically do this, one way of being able to do this is start from the requirement side. So first ask, why am I modeling? What am I modeling? Why am I observing? What am I observing? And come up with sort of a wish list. What would I really need to be able to do my job? And once you have that in place, then you can start figuring out what is realistic, what can you do, and how can you coordinate these things. But to start with the question, should I have an observationalist and a modeler work together in principle, is not a very practical question, and is more like a, by lack of better wording, creates administrative hurdles rather than scientific benefits.
So Hendrik, it seems like one thing that would be key to starting from the requirement side then, especially with respect to forecasts, is to have some of the folks in the agencies who are aiming to develop better operational models engaged in the conversation. And it seems like in agencies, you know, restrictions on budget for things like travel to come to you know, scientific meetings like Ocean Sciences that might not be well funded, but are the folks from the operational side heavily engaged in meetings like EPIC, or what do you recommend for engaging with those individuals specifically? IARPIC seems like it should be a great platform, but it seems like we have more folks at the higher levels participating, but not necessarily the on the ground folks running these operational models that could give us some details about the requirements?
Well, I've seen that you worked with Bob Grambine and others, so you have a few people. There are not that many people in the Weather Service working on this, and actually, the little bit of a game changer is that we didn't even have a requirement to do ice modeling of some ways, and so with the reorg of the Weather Service and also with the National Ice Center becoming part of the Ocean Prediction Center, we've actually went a step back and actually formulate some requirements of what we actually need. And I don't like the way it's going, in a sense that I would really like us to be practical about this. What's the parameters you need? How accurate? What resolution? What time? Space and time resolution? We don't really do that yet. But the document that is going forward now to actually establish requirements within the Weather Service for ice modeling doesn't tell me that I need to do coupled modeling, but it specifically says that the only way to have value in the high latitudes is to have a consistent ocean, atmosphere, and ice guidance. And so it's a requirement that if these things are not consistent, my forecasters can do nothing. So that screams really loudly coupled modeling, but it doesn't say it. So for me, that was very helpful, because for me, that is saying, yeah, no, we need to do coupled modeling. And actually, from my own experience, the main reason why we are not doing a coupled model on the shorter timescales is because the ice model was not consistent enough and not good enough on the short timescales. And that's why I was very happy to show you those two result slides I showed. But it is a question of going through the requirements. It actually may sound to a lot of people as being sort of an administrative type of exercise, but it really helps us to focus on what we need and what we don't need, and to step a little bit out of this community. A good example of this is that where is the big impact of an accurate weather forecast right now? The 3-4 week out, or actually the 2 to 6 weeks. We have absolutely no skill there. We have no clue what kind of science we need to actually get that better. Well, it's not that black and white, but making a dramatic point here. And but it is a real requirement, because this is where the impact is in the economy, in the safety, and especially actually in the Arctic. I mean, it takes a few weeks to get your resources out in high latitudes if you want to do any economical activity there. You have to know when you need to get your supplies in before the winter closes everything down, and so that's all on that 1-2 month time scale, not on the 1 week. And so just the recognition that we need something there, and the recognition that we don't have the science yet, is changing our focus on the work we're doing. It's a real impact. And it's not only a real impact, it has a question of, okay, House and Senate, if you tell us to do that, these are the resources we need. And guess what? We certainly get them. So it is really, really powerful doing it that way.
That's great. That's really helpful. Thanks. So I know we're coming up on actually past the end of the hour. So Hendrik, one thing I wanted to ask you is if you could say a word about the availability of the operational model code. I know when you visited Alaska last year, you talked about setting up a sandbox type of a structure to allow scientists easy access to the operational model code. Is that already happening via NCAR, or what's the timeline and the place to go for that? And then once Hendrik's finished answering that, I'll just ask Wilbert and Richard, as the modeling sub-team leads, if you've got anything else to add before we close.
So we are moving rapidly within the Weather Service to actually do all our development in an open GitHub environment. So not in-house, but available to everybody. WaveWatch 3 is completely available on GitHub now. The CIS consortium, CIS 5 and CIS 6, I don't know if 5, but CIS 6 is definitely available on GitHub. MOM 6 from GFDL is completely available, open on GitHub now, and so we're moving that way. But there's a difference between being available on GitHub and being useful. And the first sort of semi-official version of the of the UFS is the global GFS implementation of the Weather Service. You can go to GitHub and actually find it. All the data is there. And as of the end of January, there will be a supported application there available as the first step to really being able to do this. So the component models are all starting to get there, but you still need to know where they are and you still don't have the support. We hope to have the first real support in place by the end of January. And that's specifically for the FV3 version of the GFS. It may be, but not quite sure yet, a standalone regional version of the GFS. And these 6 prototypes that I mentioned on one of my slides should all be available in GitHub, but we're not quite ready for fully supporting that one yet as an application. So lots of progress, actually.
Great, thank you. And Hendrik, I'll just ask you if you wouldn't mind sending details about how to join the weekly calls with the UFS steering committee. Meredith could include them in the minutes so we can get them out to everyone.
Just go to the website that's on the front page of my slide, and it should be all the way on the front page on how to join.
Thank you. Well, I think Wilbert had to step off, and I don't know if Richard's still with us either. So I think we'll end this webinar. I'd like to remind everybody that this webinar is recorded, and so please feel free to share the link once it's posted with all of your colleagues who may be interested in listening to the conversation and then following up to continue this conversation within your collaboration teams. And please let us know if you think that it would be worthwhile to set up a self-forming team specifically for discussing marine biogeochemistry and modeling. Thanks so much, everyone. Hendrik, thank you very much for making time to give this wonderful presentation and engage in our conversation. And we look forward to continuing our discussion. Thanks so much.
Yeah, the interesting part is actually that we're really changing around because this is my job.
Bye-bye, everyone.
Thanks, everyone. Bye-bye.
Thank you.